Hi everyone, I hope you're doing well. My name is Sophia Pedigo, and today we're going to be finding an equation which relates the change in air pressure, temperature, and the change in altitude. So for starters, we're going to make a couple of assumptions in order to do this. First, we're going to be working with 1 mole of gas. The process is adiabatic, meaning there's no change in heat, and it's also a reversible process. Now, the way that we're going to do this is we're going to use these equations over here, specifically the differential change in pressure divided by the differential change in altitude is equal to negative density multiplied by the acceleration due to gravity. We've got du is equal to the change in heat of our system minus pressure times the differential change in volume. Then we have the ideal gas law, which is just PV equals RT. We've got the specific heat capacity to constant volume is equal to the change in heat divided by the change in temperature. And we've got the specific heat capacity to constant pressure is equal to CV plus the gas constant. Now we're going to start by looking at this first equation here. I'm going to rewrite it. So we have dP over dz is equal to negative rho g. We'll make a substitution in for the density, and that will give us dP over dz is equal to negative Pm over RTG. Now we can rearrange this equation and integrate both sides. And that will give us the integral from T1, some initial pressure, to T2, some final pressure, of T over P dP is equal to negative mg over r. Those are constants. They stay outside of the integral, multiplied by the integral from some initial altitude to some final altitude, dz. Now, as it turns out, we can't solve for this side of the equation yet, but we can solve for this side. So I'll go ahead and do that. This all stays the same right here. And when we solve that integral, it's just going to be dz, which is the change in altitude, all over r. Now, ultimately, what we're going to be doing here is we're going to use this equation here, my second equation, to make a substitution in for t, which will allow us to solve that integral and will give us an expression that shows the change in pressure with the change in altitude. So I'm going to rewrite this equation off to the side so we have that for later, and we can try to find an expression that we can substitute in for t next. All right, now that we've got that written down, I'm going to rewrite this equation over here. So we've got du is equal to the change in heat of our system minus the pressure times the differential change in volume. Now, earlier at the beginning of this video, I said that we're working with an adiabatic process. So that's one in which there's no change in heat in our system. So this term is just going to be equal to 0. And we can also make a substitution for du using this one, which is the specific heat capacity to constant volume is equal to dq over dt. So that is going to give us Cv dt is equal to negative. We're going to make a substitution in for the pressure using the ideal gas law. So that will be negative RT over V dV. We can rearrange this and take the integral of both sides. So when we do that, we're going to end up with CV natural log of T over T1 equal to negative R natural log of V over V1. And this is just some initial temperature T, or I'm sorry, some final temperature T divided by some initial temperature T1. And this is some final volume V divided by some initial volume V1. Now, as I said, we're trying to find an expression for T. So let's see if we can simplify this and solve for T. And when we do that, we're going to end up with T over T1 is equal to V over V1 raised to the negative R over CV. Now we're trying to find something that has temperature and pressure in it. And right now we've got temperature and volume. So let's make a substitution for volume using the ideal gas law. When we do that, we end up with T over T1 is equal to, let's see, RT over P divided by R T1 over P1. All of that is raised to the negative R over CV power. Now, the ideal gas constant is going to cancel out. But we're dealing with different temperatures and pressures because this is our final temperature and pressure and our initial temperature and pressure. So those don't cancel out. And I'm going to erase this stuff up here. All right. Now let's simplify this a little bit, clean it up. So T over T1 is going to be equal to T over T1 raised to the negative R over CV power multiplied by P1 over P also raised to the negative R over CV power. I'm going to combine these terms right here, so the T over T1, and that will give us T over T1 raised to the 1 minus R over CV plus R over CV, and that's going to be equal to P over P1 raised to the CV over R power. Now we've kind of got a messy exponent over here, and we're going to simplify that really quick. So this can really be rewritten, that one, the one over there, can be written as CV over CV plus R over CV, and then we end up with R plus CV over CV. Now, by my equation over here, which is the specific heat capacity to constant pressure is equal to CV plus R, we can substitute CP in. So we'll end up with CP over CV. Now this is a ratio of the specific heat capacity to constant pressure to the specific heat capacity at a constant volume. And I'm going to define that ratio as K. So anywhere that we have CP over CV, just going to write K. So that's going to end up giving us T over T1 to the K is equal to P over P1 to the K minus 1. We're going to simplify and solve for T. So that's going to give us T over T1 is equal to P over P1 raised to the K minus 1 over K. Then we're just going to multiply both sides by T1. And we're going to end up with T equals T1 multiplied by P over P1 to the K minus 1 over K power. And that is the expression that we're going to use to substitute into that original equation we found. In order to do that, I'm going to erase all of this. And before I actually make that substitution, I'm also going to write this equation up here, just so I don't forget it. 2, so T equals T1, P over P1, the K minus 1 over K. Okay. Let's go ahead and substitute this in for our integral and solve. So we're going to end up with the integral from some initial pressure P1 to some final pressure P2 of the equation that we just solved for, T1 multiplied by P over P1 to the K minus 1 over K divided by P dP equals negative mg, the change in altitude over R. Now, T1 and P1 are constants, so we're going to take those out of the integral, and we will get T1 multiplied by P to the 1 minus K over K, integral of P1 to P2 of P to the K minus 1 over K minus 1 dP equals negative mg delta z, or change in altitude, over R. Now, I'm going to move these constants to this side and take the integral, and when we do that, we end up with P raised to the K1 minus K over K1 minus K over K minus 1. K1 minus K over K That's going to be evaluated from P1 to P2. That's going to be equal to negative mg delta z over RT multiplied by P to the K minus 1 over K. All right. This we're just going to plug in P1 and P2 for, so we'll end up with, oh, I'm going to multiply both sides by that. So we'll end up with P2 to the K1 minus K minus P1 to the K1, K minus 1 over K equals negative mg delta z over RT multiplied by this P to the K minus 1 over K multiplied by, I'll put this here, K minus 1 over K. Okay, I'm going to erase this stuff up here so we have more room to write. And I'm going to add that P1 term to both sides. We're going to try to solve for that final pressure. So P2 is going to be equal to C P to the K minus 1 over K. And I'm going to say 1 minus mg delta z over RT multiplied by that K minus 1 over K. And close that bracket. Then we're just going to raise both sides to this. So we will end up with P2 equals P multiplied by 1 minus mg delta z K minus 1 over K over RT. This is all raised to the K minus 1 over K power. And there we have an equation that shows the variation in pressure with the change in altitude. So that's one part of this. But before, as I said at the beginning of the video, we also want to find an equation that shows the variation in temperature with altitude. So to do that, I'm going to look at this equation again. Let me just erase this so we have a little bit of room. And I'm going to rewrite this equation right up here. I'm going to label it number 3. And that is P2 is equal to the initial pressure 1 minus mg, the change in altitude, multiplied by K minus 1 over K. And that's divided by RT raised to the K minus 1 over K power. So that's part of the problem we were trying to solve. That's the variation in pressure with altitude. But now let's get the variation in temperature and altitude. So I'm going to look at this equation again, which is just T equals T1. And I'm going to substitute this expression that we just found in for that final pressure up here. So that's going to be this whole thing, which that should be P1, sorry. P1 bracket 1 minus mg change in altitude multiplied by K minus 1 over K divided by RT, and this whole thing raised to the K minus 1 over K divided by P1, and then our initial pressures cancel out and we are left with T equals T1 multiplied by 1 minus mg delta z K minus 1 over K raised to, let's see, I'll put the brackets in, K minus 1 over K. And that is our expression which shows the variation in temperature with altitude. And right up here we have an expression which shows the variation in pressure with altitude. So using only these equations and the assumptions that I stated at the beginning, we were able to find the variation in temperature and pressure with altitude.